Hi, everyone. Thank you for coming. I know it's getting late in the day. Everyone's energy is probably a little low, so I'll try and keep it lively, keep it interesting. So we're here to talk about analyzing and optimizing. So first, what I'm going to do is try and give you a little bit of motivation. Like, why is this an interesting topic? I mean, you've already been through designing, building, and deploying. And then I'm going to walk through a couple of specific scenarios in a fair amount of detail, just to show you some of the useful tools that we have available to you on the Google Cloud Platform. Specifically, some logs analysis with BigQuery, and using some machine learning technology from the open source community on our platform. So motivation. Great. In the previous session, you just launched your application. So you're done, right? You get to pack up and go home. The money just starts rolling in, and everything's great. Well, we all know it's not quite that simple, right? As soon as you launch your application, that's kind of where the real work begins. No plan actually survives contact with the end user, right? They start using your stuff in new and interesting ways that you perhaps didn't anticipate. And so you've got some challenges in this optimize and analyze phase where you want to figure out what's going on, what are your users actually doing with your product, and how do you make your product better using that information. So if you want to make your product awesome, you've got to keep working after you launch the product and use the information that your app is generating and your users are generating for you and feed that back to make your stuff even more awesome. So data is very powerful stuff. On the left side here under reporting, we see some pretty basic entry-level stuff. Like everybody should be able to know how many users do I have, how much time are they spending with my stuff, am I getting more engagement or less engagement over time? Are users churning out and churning back in? So very basic stuff on the left side, but that's kind of where you need to start. Then in the middle, we talked about this a little bit in the previous session. We've got this great thing where you can roll out an experiment to your users, and maybe 5% of them see a new UI or a new feature or some new algorithm. And you want to know, is this an improvement? Is this not an improvement? Well, if you don't measure, you'll never know. So that's kind of what we're talking about in the center here. And then on the right side, this is the really advanced stuff. Can you somehow use your own users' behavior, how they interact with your app, with your software, and feed that back into your app to provide them with an even more delightful experience? So that's kind of the advanced track there. But first, I want to give you a warning. This stuff can be tricky. It's been said there are lies, really bad lies, and statistics. Now, it's not like your app is out to trick you, right? It's not out to show you a chart to deliberately mislead you. But this stuff can be really subtle. It's very easy to draw incorrect conclusions from what you're seeing. So, be careful. This is why there is now a group of people in our industry whose business card, if they had such a thing anymore, says data scientist instead of developer. They've got a lot of the same skills and aptitudes and knowledge that developers have, but instead of building features, their core focus is gaining insights. And it's a very specialized skill set, so beware. Now, in this one session, I obviously can't make you a data scientist. I can't make you an expert in this. So that's why I'm going to focus on these two concrete scenarios to sort of give you a flavor of what this is all about. The first one is I'm going to show you the best logs analysis tool I've ever used, which is BigQuery. And then I'm going to show you how easy it is to run open source software on our platform. So, interactive logs analysis with BigQuery. As the slide says, BigQuery is awesome. In Abilana, we have an application that's implemented in App Engine, among other things, and it's generating interesting data that we want to analyze. So, unfortunately, since we just unveiled Abilana today, we don't have millions and millions and millions of lines of interesting logs to analyze for me to show you. However, lucky for me in demo land, what we've done is we imported a bunch of Wikipedia's logs into BigQuery so people could play with them and see what logs analysis is like. And Wikipedia does get a lot of traffic. So let's take a look. So here is a BigQuery interface. Excellent. And just to give you a sense of what BigQuery is like and the size of data set we're looking at, we've got a very simple query here. We just want to know how many rows are in this table, which is all the logs from January of 2012 for all Wikimedia products. So let's run that and see what we get. And so we're looking at about 1.7 billion rows of data. That's pretty good traffic for 1 month. But you'll notice here that it says, hey, that was cached. Well, obviously, I ran this query earlier. And if all I do is show you queries that I've already run and it's giving me cached results, that's kind of cheating. So I'm going to go into the options here, and I'm going to turn this off. So now it is not using cached results, and we'll do this again. And perhaps somewhat surprisingly, it doesn't actually take that much longer. But now it says something even more interesting. 4.8 seconds, 0 bytes processed. Well, that's really impressive. We can process nothing in 4.8 seconds. By now, I'm sure you're convinced that this is the best query engine in the world, right? Well, what's going on here, of course, is it just looked at the table metadata, right? It hasn't actually crunched any of the rows of the table. It didn't even have to look at the rows of the table to know how many were there. So let's do something where it'll actually have to look at the rows of the table. So what we're going to do is add something to our query here where we're still just going to do a select count star as the row count. We're still going to the same table. We've just added a where clause. And what we're doing is saying we want the project, the Wikimedia project, to be WP, which is their code for Wikipedia, because they have more than just Wikipedia. Wikipedia is just the thing everybody knows about. And language English. So now we want to say how many rows in this data set are actually for English Wikipedia out of the 1.7 billion I think we saw before. So let's run that and see if we process more than 0 bytes. And we do. Great. Amazingly, it still took about the same amount of time, which is kind of interesting. Like, it took us 4 seconds or so to process 0 bytes. Now we're doing 13.3 gigabytes in 4.2 seconds, which is a little more impressive. So maybe now you're thinking, OK, this might be something I want to use. And we got about 500 million rows. So now we're playing with 500 million rows. OK, that's interesting. Now let's do something that might actually be impressive. What we're going to do now is do kind of an interesting query. So we're adding a couple of things here. Now it's not just select count star. Now what we're doing is we're saying, all right, I want to select the title of each of the page views, and I want to sum across the number of views. So basically what I'm going to get here is a list of pages and how many times they were viewed in the month of January in 2012. OK, that's great. But down here, I've added something even more interesting, which is a regular expression match. I'm only interested in the pages where the title matches this regular expression, which in English means it starts with an uppercase G, there's a lowercase o somewhere in the middle of the word, and it ends with a lowercase e. And I can think of at least one word that fits that description. And at the bottom, we're just finishing off with the group by title and order by views. So basically what we're going to get is we're going to see the top results first. So let's run this one. Now, I just want to make note here. 13.3 gigabytes is what the previous query processed. So now, this will probably take a little bit longer. It's doing a little more work. After all, I'm running a regular expression over 500 million rows right now. Oh, it's done. So that's faster than grep, for sure. Much faster than grep. So, but look at this. Now it processed 72.7 gigabytes in 8.8 seconds. So what's going on? Why did this process more data than the previous query? Well, we added a column, right? We added this title column to the query. So it had to look at more data to do what I was asking it to do. Well, that's great. I mean, 500 million rows, that's pretty impressive. Going through 72 gigabytes of data in 8 seconds, that's pretty impressive. But it's not quite impressive enough. I don't think I've convinced you yet that this is the greatest logs analysis tool in history quite yet. So let's look at 6 months of logs. So this is the first 6 months of 2012. And this is the same query as, not the one I just ran, but the one previous that just tells me how many rows am I going to be looking at. And what you can see here is in the rest of the query is exactly the same. All I've done is add in the from section, I'm referencing 6 tables. This is actually a very common pattern with how people put their logs into BigQuery. They, depending on how large their logs are and how much traffic they get, they will do 1 month per table or 1 day per table, for example. And then you can, and what BigQuery allows you to do is say, well, I want you to look at these 6 tables or these 10 tables or these 20 tables. So it's like it's one big table when you use this syntax. So let's give that a go. Now we're going to go over, well, let's find out how many rows we're going to go over. Now, this took like 4 seconds before, and now we're doing 6 times the data, so it should take 6 times as long, right? Well, that math didn't work. But, 6 seconds, 78 gigabytes, and we're looking now at almost 3 billion rows. OK, so let's run a regular expression across 3 billion rows. So we have our same query here as before. We're going to do the aggregation we were talking about. But we're hitting the 6 months worth of data, and we're doing the same regular expression. So again, this took, what, 8, 9 seconds last time? So it should take 6 times as long, right? So 6 times as long, that would be about 40, 50 seconds, right? That's kind of what, if it's scaled linearly, that's what we would be expecting to happen. But it only takes 12 seconds. And it processed 430 gigabytes. That's almost a half a terabyte in 11.7 seconds. I mean, just reading this much data off a hard drive, the best hard drive you can find, is going to take like 17, 18 minutes, I think. I did the math a little while back on that because I wanted to know, is this really that impressive? But you buy the fastest SSD you can, you read the data from it as fast as you can, it's still going to take you nearly 20 minutes just to read it, much less running the aggregations and the regular expressions and all that. And BigQuery did it in less than 12 seconds. So hopefully by now, you agree with me. If I could switch back to the slides, please. That BigQuery is awesome. So how is it that BigQuery can do this awesome thing I just showed you? What is this magic where I throw 6 times as much data at it, nearly half a terabyte, 3 billion rows, and it runs this regular expression across 3 billion rows in less than 12 seconds? How does it do this thing? Well, back in 2010, we published this paper on something called Dremel. Dremel is the internal name for the technology that became BigQuery. And this was developed to do exactly what I just showed you. It's developed to do interactive scale analysis, interactive speed analysis of the huge data sets we had to deal with at Google. So what do I mean by interactive? Interactive means, well, in this context, it means I can stall up here on stage long enough for the query to end, right? In this context, that's what interactive means. But in a real context, what it means is you don't feel the need to get up from your desk and go get a coffee while your query runs. Or worse yet, switch off to that other project that you have on the back burner and bring it to the front burner and completely lose your productivity. Interactive means it's fast enough that you don't lose your train of thought. So there's a few key points that I want to cover that are in this paper. I encourage you to go read it. It's great reading. There's a few key points I want to cover from this paper that will help you understand where BigQuery is really going to shine, like where you should really use it. So the first is BigQuery uses this multi-level serving tree. This is if you think about the regular expression that we were just talking about, this is a classic divide and conquer sort of problem. I can just take my 3 billion rows, chop it up into lots and lots of little pieces, and then farm it out to all these leaf nodes where each leaf node can process its little piece of the problem in a few seconds, right? And then it can say, well, of the 100,000 rows or the million rows you gave me, here are the few that matched this regular expression. And they pass that up to these intermediate servers. And then the intermediate servers can bring these subsets together. But in this case, we're not actually passing back up. In the query I showed you, we're not passing back up the actual matching rows. What we're doing is we're counting the rows that match. So the leaf nodes do all that counting. And then they just pass up their counts to the intermediate servers, which then just add those counts together, which is really fast. Computers add pretty well. And eventually it gets up to the root server, and we have our answer. So this multi-level serving tree is sort of where that magic happens. That's why you can imagine when we went from 500 million rows to 6 billion rows, the reason it only got a little bit longer was because this tree got so much wider. We just split the data up into way, way, way more pieces, and they still took about the same amount. And then we took a little extra time in the intermediate servers because they had a little more work to do to combine all these sub-pieces. So the takeaway from this is BigQuery really shines when your output set is much, much, much smaller than your input set. And there is a huge number of very useful queries that meet that description. For example, the whole needle in the haystack thing. It's like, I remember doing this when I worked on cloud storage. We would be trying to debug a problem with a particular object, and I could go through months' worth of logs and say, show me everything that ever happened to this particular object. And I could see when it was created, when it was accessed, and so on, and then figure out what happened. And that's really powerful because I was able to go over these billions of rows of records and just extract just the information that was relevant to my problem. That's the sort of thing we use Dremel for internally, and that you could use BigQuery for over your logs. Aggregation is another example of this type of query where you're looking at a lot of data, but you're actually bubbling up relatively small amounts of information. The second piece of technology that underpins Dremel and thus BigQuery is column-oriented storage. So in a lot of really useful data sets, you have a lot of columns, maybe hundreds of columns. And if you're storing them, like you see on the left here, in a row-oriented way, even if you're only interested in a few of those columns, you have to read the whole row off of disk, throw most of that data away, and then read the information you're interested in. If instead you can somehow figure out a way to store the columns together instead of the rows, and you're only interested in 5 out of 100 columns, you just read those 5 columns, and that's it. Another similar example is sometimes the data is very sparse in that there's a column that only appears in 1% of your records, for example. But if you store it as rows, you have to read the whole row just to find out, oh, this one doesn't have the column. If you store them in this column format, then suddenly you only look at the data you need. Now, you remember I made a point of saying when we added the title column to our query, suddenly the amount of data we processed went from like 13 gigabytes to 70 gigabytes or something like that, 78. That's where you can see this column-oriented storage in action. BigQuery only looks at the data it needs to look at to answer the question you asked it. So when I asked about the title, suddenly it had to look at more data, and it's telling me how much it needed to look at. Now, the trick with doing this well is being able to efficiently translate between row and column-oriented storage. And if you're interested in how that works, I can't really explain it, but the paper does a great job of that. So we talked about the multi-level serving tree. We talked about the column-oriented storage. If you're someone who has worked with large analytical databases before of a certain type, or if you're somebody who's got a lot of relational database experience, you're probably asking yourself, sure, but what he did before this talk was he created indexes on those things that he was querying on. Well, here's the thing. For this large class of queries where the output is much, much smaller than the input, you don't need, if you use these two tricks, if you use the multi-level serving tree and you use the column-oriented storage, you don't need to have an index. You just look at all of the data and you get your answer. And you can do it really, really fast, as I've shown you. So this allows you, you don't have to decide in advance, well, these are the interesting columns and in this order. You don't need to figure that out before you start asking your questions. You just start asking your questions. BigQuery looks at the data it needs to look at to answer them in a very fast and efficient way. And then you just follow your data where it leads you. So the demo I showed was the BigQuery browser. That's the thing in the top left here. And it's a great tool. It's the best way to get started with BigQuery and see what it can do for you. But at its core, BigQuery is not that UI I showed you. BigQuery is an API. BigQuery is a service that you access through this API. So that means not only is there this BigQuery browser that I showed you, but there's a command line tool. So if you're the type of person who thinks the mouse is the device you use to point at the console in which you want to type, then you're probably going to like the command line tool. If you're the sort of person who lives and breathes and is in Excel all day long, creating reports and generating spreadsheets, we've got a connector for Excel where you can pull, like run a BigQuery query and pull the results into Excel. Now, of course, because it's an API, we're not the only people who can build cool UI on top of it. So there's this long list of people in the middle here who have integrated their products with BigQuery. And at the top of that list is Tableau. And down in the vendor expo, you can find, they've got a spot set up there. And just the other day, Jeff down there was showing me this fantastic demo of analyzing the GDELT data set, which we have. It's another one of the interesting public data sets that's in BigQuery with this great, geo visualization and colors and all sorts of stuff. I encourage you to go take a look at it. It's really cool stuff. And then finally, on the right side here is whatever you guys build. Remember, it's an API. That means you can write code to submit queries. So you're not limited to what we built or what some third party built. You can build your own dashboards for your own business. You can integrate this into your products if you want to. So hopefully you're sold, right? You agree with me that BigQuery rocks. You want to use it to analyze your application and see what's going on. But there's one downer. And in fact, an audience member pointed this out in the previous session. He asked the very great question. It's like, so how do I get my App Engine logs into BigQuery? And the answer was, come to this session, and we'll tell you all about it. So now that's what I'm going to do. In the context of Abelana, we've got some App Engine logs that server is creating. We've also got some interesting data in the data store that you might want to link to those logs. Like, for example, the users you have, what photos they've chosen to like, and so on. And we also, you'll recall from the previous sessions that Abelana reads and writes photos directly from cloud storage, not via App Engine. Like the Android app interacts directly with cloud storage. So cloud storage also has logs that you probably want to analyze. So you want to get all of these things into BigQuery so you can do the sorts of things I was just showing you. So how do we do that? Well, this is where stuff gets real, right? At some future date, I want to give a version of this presentation where I can say, go click these 3 checkboxes and it'll all show up. Unfortunately, today is not the day I get to give that presentation. Today is the day where I tell you there's a little bit of work to do to load this data into BigQuery. Fortunately, we have published some best practices about these, about how to do this. So I'm going to walk you through those now and then give you a pointer on how you can stay up to date as these things get better over time. I think there was a question about, well, how soon will this be automatic? And somebody who runs that team gave the answer, sometime this year. I think the comment was, it'll be a Christmas present. So let's talk about the easiest one first. Cloud storage. So BigQuery already loads data from cloud storage. What I mean is if you want to put your data into cloud storage, if you have some big file you want to analyze with BigQuery, you upload it to cloud storage and then do a load job into BigQuery. So that's sort of the normal way to load your data. So what you can do with cloud storage is there's a feature where you can just enable log delivery. And you tell cloud storage, hey, I want to know everything that's going on in this bucket here. So we might do the Abelana in and the Abelana out buckets. Say, I want to know everything that's going on in these 2 buckets, and I want you to put those logs in this Abelana logs bucket. And then every hour, a new object will show up in that bucket, which contains all the activity that happened on the other ones. Then you can run a load job, get that into BigQuery, and do the sorts of things I was showing you. So next up, let's talk about App Engine logs. In this case, what you need to do, there's a logs read API. You need to use the App Engine MapReduce library to do a MapReduce over that logs API, get that data into cloud storage in a format that can be loaded into BigQuery. Fortunately, you don't have to write this from scratch. In fact, 2 people have already written it for you. There are 2 open source projects. One's called Log2BQ, and the other one's called Mash or Mache. I'm not sure how they like to pronounce it. That will do exactly this pattern for you. One's written in Python, one's written in Java. Choose your favorite language and go. And then finally, Cloud Data Store. This is where we have our users and likes information that we want to import in. You may be noticing a pattern here. It's like, do a MapReduce, get it into cloud storage, load it into BigQuery. In this case, we don't have an open source project I can point you to, but we do have a code lab, which basically walks you through it step by step. So those are the patterns. That's the best practices. That's what you can do when you leave this door tonight, go home, and this will work. This is what you can do today. Hopefully very soon, sounds like perhaps this quarter, at least some of this will start to get easier, and I expect it to get easier and easier over time. So when in doubt, go read the docs. Everything I just told you in the previous 3 slides was pulled directly from this documentation page. Watch this space for updates, because this is where you'll find out that, oh, by the way, now it's just a checkbox. So our first example is complete. Hopefully, I've made a good case for how BigQuery is a great tool for analyzing your logs and giving you some pointers on how to get to the place where you can do that. Now let's talk about something completely different. So Avilana has this thing called a photo feed. And in fact, earlier today in the second session, Frances talked about how, today Avilana assembles this photo feed in a fairly, how would I describe it? It's kind of a straightforward thing. It's like, well, you follow these people, they upload photos, therefore it shows up in your photo feed, right? And it's just strictly chronological. Well, this is a wonderful opportunity to improve the user experience through watching their behavior, right? Can we come up with some clever way of deciding what things show up in the photo feed higher and lower, or which show up and don't show up at all, that will tend to show people images that delight them versus images that bore them? So this has a huge impact on the experience people are going to have with this application. It's a really big deal. So everyone in this audience could probably come up with fantastic ideas for how to make this better, right? You could, if you're an image processing person, then you're probably going to say, well, you could extract all these features and photos that are bright or that are outdoor stuff. Those are always going to be big hits. Photos with people in them, or maybe you want to detect cats because everyone loves cats, and we'll just promote all the cat photos to the top of the feed. Everybody could have an idea for this, and they're all good ideas, right? And you could actually implement some of them, and you could do the A/B testing we were talking about, where you deploy this as an experiment and see, well, do people click, do more likes when I use this algorithm versus that algorithm? But for today, what we're going to do is talk about collaborative filtering. Collaborative filtering is a class of machine learning algorithm that is used to predict user preferences. So, for example, you're on a retail site and you choose to purchase item A. And generally speaking, you get a list of other items that that retailer would love to sell you that they think you might be interested in because you are interested in item A. The way they do that is they notice that people who buy item A, they kind of often buy items B and C as well. This is a classic collaborative filtering task. A similar scenario is if you're on a movie site and you rate movie A with 5 stars, then it might suggest some other movies you might like, and they know that because other users who rated this movie 5 stars also rated those other movies highly. So for example, the Netflix prize competition was a collaborative filtering machine learning competition. So what we have in Avilana is photos and likes, right? Users can click like on a photo. If there are other users around that have a tendency to like the same photos that you do, then when they like a photo, it's kind of a good bet that you might like that photo. And so we could come up with a collaborative filtering model which could then promote these images that we think you're likely to like higher in your feed. But the bad news is I don't have a PhD in machine learning. So I can't write a collaborative filtering algorithm. It would be touch and go if I were to even read a paper and try and implement a collaborative filtering algorithm, because this stuff is difficult to understand, difficult to write, and really difficult to verify that it's working properly. So what I want is a library that somebody else has written, somebody who does have a PhD in this stuff has written, and has tested, and has been used elsewhere, and I know it works. That's what I'm looking for. So this is where open source can help a lot. You do a little bit of Google searching, and you find out, hey, there's this thing called MLlib, which has a collaborative filtering algorithm in it. And it runs on this thing called Spark, which runs on Hadoop. So all I need is a Spark cluster. Where do I get a Spark cluster? Well, that I can help you with. So let's deploy Spark on Hadoop 2 different ways. We're going to do it the easy way, and we're going to do it the even easier way. So here is the easy way. So this is using a utility that Google created called BDUtil, stands for Big Data Utility, which is, its purpose in life is to deploy Hadoop clusters on our infrastructure. And I'm telling it to add this extension, Spark Shark, which tells it, oh, by the way, I want my Hadoop cluster to also have Spark on it. I configured a file earlier which tells it, the bucket I want it to use, the project, what zone it should be in, what machine types to use, how many worker nodes, and stuff like that. This is all pretty close to the default settings, so I'll just let that start. So what it's doing now is it's going to create these VMs, SSH into them, install all the Hadoop stuff on it, install all the Spark stuff on it for me. And then, when it's done, I should have a fully functioning cluster. But it's going to take a few minutes. So while that's running, what I'm going to do is show you the even easier way to do this, which would be using click to deploy, which you saw earlier in Francesc's talk, where he did a click to deploy of Redis on our service. So down here in the compute section, under click to deploy, we can see Apache Hadoop. And as Francesc noticed earlier, it's actually 2 clicks, because you got to click go first, then you have to click deploy cluster. Now in this case, sure, US Central 1A is fine, 2 worker nodes will be fine. Tell it the bucket I want to use. And look at that, there's a checkbox for install Apache Spark. That is so convenient. Down here you can see that if you want to, you can use larger or smaller instances for reasons that hopefully I'll be able to explain later. High memory instances can be particularly interesting for Spark clusters or clusters where you intend to run Spark, but I'm just going to leave all this stuff as default for now and click deploy cluster. So deployment may take 3 to 10 minutes. We've got 17 and a half left, so hopefully before the end of the talk this will be done. So I'm just going to leave that running. Come back over here and we can see, all right, it's, the script has successfully created the VMs. And it's now in the process of installing the Hadoop software on these nodes. So while this is running, I'm going to switch back to the presentation, please, and talk just a little bit more about what it is we're setting up here. So we have these 2 clusters coming up. What is this? What is this stuff that I'm currently bringing up? Well, let's go back in time a little bit. 2003, Google publishes a paper on something called the Google File System. The Google File System is a cluster-level distributed file system. This is something that any serious distributed computation over very large data sets, you've got to have a distributed file system to do that. Because if you're always trying to go back to one machine or one file server or one SQL server or something like that, it's never going to scale to the truly large data sets. And then in 2004, we published another paper on MapReduce, which provided a programming model which was really useful for a large variety of workloads, search indexing being one of them, which ran on the Google File System and did a lot of good stuff for us. But if you didn't work at Google, you didn't get to play with these toys. So the open source community said, hey, this stuff looks good, we want some. So they started to implement things that looked a lot like the Google File System and looked a lot like MapReduce. And there was a variety of implementations, but the most popular one, of course, is Hadoop. And so Hadoop, at its core, is an implementation of MapReduce with an implementation of a distributed file system called HDFS, which looks a whole lot like GFS did. And you can't spend very long around talking about Hadoop before encountering all of these references to elephants and so on. So that's why I put the logo up here, so you could see, OK, that's where all the elephant references come from. Now, of course, at Google, GFS and MapReduce were great, but they weren't sufficient, right? That's not everything that we have there. I've already talked about Dremel, right? But we also have this thing called Bigtable, another thing called Megastore, another thing called Spanner, another thing called Chubby. All of them fill in different niches in this large-scale distributed computing space. So similarly, in the open source world, people don't talk about Hadoop as just MapReduce and a distributed file system. They talk about Hadoop as an entire ecosystem of things, each of which does its own very specialized thing. So I could go through each of these things and tell you what they are, and that wouldn't be much good to you. For the purposes of this talk, these are the ones we're talking about, like the core Hadoop distribution, HDFS, which is the distributed file system, and Spark, which is the thing that has this library that we wanted to use. So what has Google added to this, right? How have we made it better to run Hadoop on our platform than perhaps to like buy a bunch of machines and rack them and run them on your space? Well, the first thing we've done is we've built these connectors that you can use to read and write from our managed storage services from your Hadoop jobs. HDFS is not just a file system implementation, but it's also an interface that all these pieces, all those buzzwords you saw on that previous slide, use to talk to the data storage layer. So our these connectors basically make our storage services look just like the native HDFS file system. So all of those buzzwords can read and write from our storage services just like they were reading and writing from the native HDFS file system. This is super powerful for two reasons. One, we're bringing up a brand new cluster right now in the background. When that cluster is up, the HDFS file system will be completely empty. That means in order to do any useful work, the first thing you have to do is import all your data into HDFS, and then you can actually do something useful. If your data is already sitting in cloud storage, you can completely skip that step. You can just start doing useful work reading the data from cloud storage. And the second reason it's powerful is because when you're done processing your data, if you do it with the native HDFS file system, then you have all this output sitting in your file system, and you have to keep your cluster up just so you can read your data. So you're paying for all of these CPU and memory resources that you're not using, that are sitting idle, just so you can read from your distributed file system. If instead you write your final results back to Google Cloud Storage, as soon as your job is done, you just tear down the cluster, and then you're paying nothing. So you only pay for the computation you need. So, and as I mentioned earlier, this applies not just to MapReduce jobs, but to all those things you saw on the previous slide. So the other thing we've done is the two things I demoed earlier, which is BDUtil, Big Data Utility, and Click to Deploy. Click to Deploy is a great place to start, right? It brings up a totally functional cluster that you can go in and kick the tires and play around with. It's easy to bring the clusters up. It's easy to bring them down. So that's a great place to start. If you have some more advanced scenarios in mind, like I really like this one thing, or I want to customize it in this one specialized way, BDUtil is probably the place you're going to end up eventually, because it is a script. You can go in there and modify it. You can create your own extensions, like you saw the Spark extension I used. It's also, obviously, it's a command line tool, so it's very, very scriptable. So finally, what is Spark? Because I've sort of told you, well, Hadoop is the MapReduce, and HDFS is GFS, but I haven't told you what Spark is. Spark's relatively new. It was developed down here in the Bay Area, in the Berkeley Amp Lab, and has since been transferred to become its own top-level Apache project. The key concept in Spark is this thing called a resilient distributed data set, or RDD. What they were attempting to do with Spark is they looked at the pattern of computations that didn't fit the traditional MapReduce model very well, and they said, what we'd love to do is sort of pull all this data into memory and then iterate on it really fast, right? We think that the working set on this calculation is small enough that we can actually fit not on the memory of one machine, but we can fit it in the memory of a large cluster. So how do we distribute this data set across all of these nodes in a resilient way such that if a node goes down, it's not lost? We can still read it from secondary storage and bring it back up. So the RDD is all about how they make that work. This is a huge win for certain types of workloads, particularly this iterative workload where you're going over and over and over the same data often. And training machine learning models tends to be a very iterative thing. So this model works really well for machine learning. So now we have more buzzwords, right? Because Spark is starting to build its own ecosystem around itself. One is Spark SQL. It used to be called Shark. That's a SQL-like interface. So if your data set will fit into memory on your cluster, then you can run these SQL queries across it very, very quickly. Now, if it doesn't fit into memory, you can still run the queries. It's just going to be a little slower. There's a streaming processing library. There's a graph processing library. And there's this thing called MLlib, which is the thing we actually wanted at the start of this presentation. And it includes the alternating least squares, ALS, collaborative filtering algorithm. And because this is running on Hadoop, it reads and writes from HDFS, so it can read and write from via all our connectors. So, demo time. What I'd like to show you is how I was able to take this library and build collaborative filtering into Abelana. And then you're all going to take out your phones and you're going to see this awesome, delightful set of photos based on your personal preferences and so on. But I'm not that good. So what I'm actually going to do is just show you that we have, in fact, brought up a fully functioning Spark cluster here. And I'm going to do that by walking through a slightly modified version of the collaborative filtering example that's in the Spark documentation. So what we see on the screen now is the end of my BDUtil run. And I can see that it has completed, and it looks like it completed successfully. So what I'm going to do now is BDUtil has this nice feature where it can bring up a SOX proxy for you. And then if you point a browser to this SOX proxy running on your local machine, it proxies all those requests over to your compute engine network so that you can do something that looks like this. And lo and behold, you're looking at the Spark master on your cluster, and you're doing it by name. Notice in the, wow, that's small. Up there in the upper left corner, it actually says Hadoop-M. I didn't have to do that by IP address. That makes it really easy to do things like click on these links, and all these links will just work. You don't have to open up any ports on your firewall. You don't have to copy and paste IP addresses and things like that. So here we have our Spark cluster. And because I'm not nearly as good as Francesc is, I'm actually going to have to copy and paste my examples. So let's use the BDUtil shell command, which is just shorthand for please SSH me into the master node of my Hadoop cluster. And then I'm going to just show you the very small test data set that we're using for this example. So what we have going on here is each row, the first number is the user ID, the second number is an item, and the third number is a rating. So user number 1 rates item number 2 a 1. User number 1 rates item number 3 a 5, and so on. This data set was chosen such that user 1 is a lot like user 2 and nothing like user 3 and 4. So I should be able to throw the algorithm at this, and it will be able to tell me, will user 1 like item 1? So let's see if we can do that. I will fire up something called the Spark shell. And the Spark shell gives me a Scala prompt which interacts with the cluster. There we have it. So if I go over to my my master node here, I'll see, hey, look, I've got a running application now. It's called Spark Shell, and it's taken 4 cores, and it has nearly 12 gigs of memory per node, right? So I now have this Spark Shell which has access to all the resources on my cluster, but I'm interacting with it like I was just, sort of typing on a local machine. So that's kind of cool. So let's just import some libraries we'll need. There's the ALS library that we're looking for. There we go. And now let's load our data. So look, we have an RDD. It has just pulled that file out of cloud storage, and it has turned it into a resilient distributed data set that can be used by Spark. Well, that's kind of cool. So let's go over here and see what the Spark shell did to do that. Well, that's kind of interesting. It doesn't seem to have done anything. right? Because there's nothing completed, nothing failed. Well, I guess just reading doesn't count, so let's try something else. Here, we'll transform that into a format that is suitable for actually building the model. So that must have done something. Nope. OK. Well, I can get behind that. Now we're going to train the model. So this is actually building the machine learning model off of our data set. So please train that model. Well, look at all that output. It must have done something now, right? Still nothing. So at this point, I'm getting a little confused, right? It's like, how is it that I trained a model and Spark still hasn't actually done any work? This doesn't make any sense to me. And this is one of the really interesting things about Spark. Spark does not actually do any work until you ask it a question that it can't answer without doing that work. All it's done so far, it's basically said, OK, at some point in the future, you might ask for that RDD. Well, I know where to get it. I know how to make it, right? Because you told me, go read it from this file. And at some point, you might actually ask me to use this model you told me to train. But you haven't asked me to use it yet. So I'm not going to go train it until you actually want me to use it. Now what I'm going to do is ask it for a prediction. I'm going to ask it, please predict what user 1 will think of item number 1. And if this works, I should get an answer that's close to 5, because that would be consistent with the other user that sort of liked the same things. So let's ask it for this prediction. Now we see tons of output. And if we go over here, we'll find now we've got things going on, right? Here are all the steps that it had basically queued up and said, OK, when you ask me for something, I know what to do. I know how to create this answer. And you can see, even though this isn't a difficult, like the input set wasn't huge, it actually distributed that load over all 8 cores on my little baby cluster. And if we click on one of these jobs, or these stages, as they call them, we can see all these statistics about what it was doing and how long it took and so on. So let's go back and see what our answer was. And indeed, we got an answer that was pretty close to 5. So we have a fully functioning Spark cluster. So the point of this demo was not that that was the most awesome machine learning demo ever. The real core of the demo was, hey, look how easy it is to pull these cool resources into your computing world and start to play with them. But the last thought I'd like to leave you with is that there's more than one way to do it. So I spent a lot of time in this presentation talking about how awesome BigQuery is at analyzing logs. But you know what? There's a lot of people who are doing a lot of great work analyzing logs using some of the open source technologies that were on one of the previous slides. That's a perfectly valid way to do that. And if you want to do that on our cloud platform, we'd love to have you do it here. And similarly, even though I was showing how you can use these great machine learning libraries from the open source community on our cloud platform, at a previous show at Google I/O, Felipe Hoffa over here did this fantastic demo where they were showing how they were going to predict the outcome of World Cup soccer games using BigQuery. So you can do machine learning on BigQuery too. There's more than one way to do it. So my goal wasn't to say, for logs analysis, you must use BigQuery, and for machine learning, you must use Spark. That's not the point at all. What I was hoping to do with this presentation is inspire you to analyze and optimize your application. And give you some starting points. Like, these are good basic starting points where you can begin experimenting. And if you take these tools and you think about your data and you get it into a form where you can do this analysis and optimization, you can really make your app awesome over time. Thank you very much.